Hello everyone, this is Mr. Fawcett, and today's lesson is going to deal with specifically reviewing our limit strategies that we've talked about in the previous few videos. So we're going to look at a couple different limit expressions and try to make some inferences as to what path we should take when it comes to evaluating the limit. Because now we kind of want to put all these strategies together and have to choose which ones are going to be more efficient for certain limit expressions versus other ones. The first thing we're going to do is I'm actually going to have you all look at these four limit expressions, and you'll notice that x is not approaching, or theta in two of these cases, is not approaching a specific value. I just have the variable a in there because my goal is not for you to actually work through all of these limits, but rather just think about what path you would take to try to evaluate them if a was a given number. So think about the first step you would take, but say that first step doesn't work, think about what other strategies you may need to employ. Okay, so give it a thorough thought, give each one a thorough going over, and write down your thoughts, and then we'll come back and do a little wrap-up discussion on each one. Okay, hopefully you've had time to think through all four of these, and you should have, for your first step for all of these, be direct substitution, right? Because the first thing we want to do when we are trying to evaluate a limit is perform direct substitution. The great thing about direct substitution is sometimes it just works and we come up with a real number, and that is going to be the answer to our limit, and we don't have to try some of these other more complicated techniques. Of course, many times it does not work, and we are required to employ another strategy. So in number one, if direct substitution did not work, there are a couple different things we may see. We may see an indeterminate form, right, where the limit of the numerator and the limit of the denominator are both equal to 0, and we get that indeterminate form, and we have to try to employ another strategy. However, in this case specifically, there is no number that would make both the numerator and the denominator both equal to 0. So that we would never have an indeterminate form here. Now, we could have another scenario where the denominator is equal to 0. So suppose a was equal to -1. Well, then our numerator would be -1 and our denominator would be 0. And if our denominator is equal to 0 and our numerator is some other number, well, we know that that's likely going to be a vertical asymptote, right? So either direct substitution is going to give us an answer right away, or in this expression, we may end up having a vertical asymptote. So step one, direct substitution. If denominator, oh, that was not great. So if the denominator equals 0, then check for vertical asymptote. All right. Number two, same thing. We would apply direct substitution, and if it works, great. If it doesn't, there's a decent chance here that we may have an indeterminate form. So if we have an indeterminate form, then what strategy does it look like we should try to employ? So should we factor, should we try to rationalize, or should we try to use some sort of trig manipulation? And as you look at both this numerator and the denominator, factoring should jump out at you, right? We have a quadratic trinomial in our numerator that can be factored, and we have a difference of two squares in our denominator. So in this case, if indeterminate form, try factoring and simplifying. And then don't forget, once we're done factoring and simplifying, we still have to come full circle back to direct substitution. So regardless of what happens, if we come up with an indeterminate form, we're going to have to eventually get back to direct substitution at the end. Now, there is a possibility here that we could run into another vertical asymptote scenario. So if the numerator was equal to some other number than 0 and the denominator is equal to 0, then we would look for that vertical asymptote, just like we did in number 1. But if we had an indeterminate form, then we would look to factor and simplify before substituting in again. Okay, let's look at 3 and 4. We should start to see a pattern. We're of course going to start off with that direct substitution. Now if it works, that's fantastic. If it doesn't, and let's say if we get an indeterminate form, what strategy does it look like we should employ here? In this case, we see that there's a radical in the denominator. And whenever you see a radical, there's a good chance that we're going to need to rationalize wherever the radical is. So sometimes we rationalize the numerator, sometimes we rationalize the denominator. And to rationalize, if we go back to a previous lesson, we're going to need to multiply both the numerator and the denominator by the conjugate of wherever the radical is. Right? So again, if we check for indeterminate forms, and then we would multiply by the square root of x plus 2 over the square root of x plus 2, and hopefully we'd be able to simplify those expressions so we can use substitution again. So if we get an indeterminate form, then rationalize using conjugates. And then of course we would simplify and perform direct substitution again. As we move on to number 4, we see that this limit expression involves some trig functions. It does not mean we're going to stray from our direct substitution attempts to begin with, but it does mean if we have an indeterminate form here, then there's actually a couple different strategies we can try to employ. So the tricky thing about trig function limits is that there's always another way to rewrite them, right? I can always rewrite sine or cosine squared as something else, or tangent, etc. Or most of the time we can, right? But not always will that help us simplify. So we may have to try a few different trig manipulations or trig substitutions before we get somewhere where we can simplify and then perform direct substitution again. It also may be the case that we need a factor. So if we just take a look at this numerator up here, we could factor that because it's a difference of 2 squares, or we could use the Pythagorean trig identity to make a substitution. Right? So either of those are acceptable mathematically, but only one of them will really help us simplify with our denominator. So again, more things to try out when you have limits with trig functions, mainly though being factoring and using trig identities or different trig formulas. So we'll try trig, manipulation, and or factoring. Hopefully we're able to then simplify and then use direct substitution again. So of course for all of these, and we talked about number 1, we may not get an indeterminate form. We may get a vertical asymptote type scenario. Again, that's kind of its own separate thing, because once we see that the denominator is equal to 0, but the numerator is not, we can kind of jump straight to vertical asymptote. Whereas with indeterminate form, we have several different things we still need to do before we figure out what the limit is going to be. I have a chart for you at the end of your notes, so we're going to go there for a second. And it basically is just a framework for how you can approach these types of problems. So it starts off, it talks about trying direct substitution to begin with. And then once you try direct substitution, you have 3 different things that could happen, right? You could have the denominator be equal to 0 and the numerator not, and then you probably have a vertical asymptote. You could have the substitution produce a real number where you're pretty much done, as long as the function is continuous at that point. And you could also have an indeterminate form, right? Which, if you have this indeterminate form, you're going to have some more work to do, which if you scroll down, I don't know how far down I can go. We'll go down to here. No, we'll go all the way down. So if you have an indeterminate form, these are the 3 options that we've been working on the last couple of videos, factoring, conjugates, and trig identities. And again, by using one of those, your goal is to simplify the limit expression so that you can eventually try direct substitution again, which is what this step is talking about. Right, so when they say try evaluating the limit in its new form, they just mean try substituting again. If all else fails, right, you can always try to approximate the limit using graphs and tables, which is what we first started out doing before we learned these algebraic techniques. But generally, one of these methods is going to work for you. You may just need to try a couple different ones before you're able to manipulate the expression to where you're able to simplify. Okay, so this was a bit of a shorter video. There are some chances up above for you to come up with your own limit expressions. So you're kind of working backwards now. You're not trying to evaluate them, but you're trying to create them from scratch, which is a pretty good exercise. So take a shot at those. If you have other problems to finish up from previous lessons or homeworks, feel free to use this framework guide as you work through those to help keep you on track. Otherwise, this is Mr. Fawcett. Enjoy the rest of your day.